All right, folks, continuing our journey here. In section 8.2, we are going to look at level curves and contour maps. It also says in cross-sectional analysis, but we're just going to focus on level curves and contour maps in section 8.2. And that matches up with Objective 1, determine a level curve, and Objective 2, construct a contour map. So cross-sectional analysis, it can be used to help us visualize these difficult surfaces in 3 space. I mean, it's really difficult to draw a 3-dimensional graph on paper or on the board on a 2-dimensional surface. If you really want to see these 3D graphs, you need to use some powerful computer software. So one way we can get around it is by making what's called a cross-sectional analysis. For example, a topographical map is a 2D graph of a 3D surface, and it uses contour lines. In mathematics, we call those level curves, that connect points that have the same elevation. And then where the close lines will indicate a steeper terrain. So the more tightly packed the lines are on a topographical map means you have a more rapid change in elevation. A collection of contour lines is called a contour map. So here's an example. In this figure at the top, we can see there's like a valley and 2 hilltops there. Looks like a little bay as well. And then at the bottom, that's the topographical map of that 3-dimensional surface we see. So contour lines are drawn. They make a contour map. In geology, it's called a topographical map. And the more closely together those lines are means the more steep the terrain is. So a topographical map does give us a way to visualize the 3D map. So how do we do that with what we're about to look at here in section 8.2? Well, we're going to focus in 8.2 just on the production function aspect of things. So let's look at this example. The production function associated with the manufacturing of a popular toy for kids is given by, and there's the production function. Q equals a function of x and y. And it equals 4.28 x to the 0.8, y to the 0.2. So remember, in a production function, Q represents quantity, and it's a function of 2 independent variables, x and y. So here, Q represents the number of toys made each week. X represents the number of labor hours each week. And y is the weekly usage of capital investment. So our question, what combinations of labor hours and usage of capital investment are needed to produce 100 toys? Well, as you can imagine, there are an infinite number of combinations of x and y that would have a Q value of 100. There are an infinite number of combinations of x and y that will result in producing 100 toys. That 100, when we see 100 toys, that's the quantity. So really what we're doing here is we're going to put that 100 into our production function where we see Q. And that gives us something like this. Now see, that's a function of, or that equation is in terms of x and y. There are an infinite number of values for x and y that makes that equation true. Well, the best way to represent all of those infinite number of combinations of x and y is by making a graph. And we can graph that in our familiar xy plane. But in order to graph that in the xy plane, and I will use my graphing calculator to graph it, when you use your graphing calculator to make a graph, everything is in the form y equals some function of x. So I have to take this equation and I have to solve it for y. My first step in solving for y would be divide both sides of the equation by 4.28x to the 0.8. And when I do that, I get 100 over 4.28 x to the 0.8 equals y to the 0.2. And I could look at that on the right-hand side, that y to the 0.2. Well, 0.2 is the fraction 1/5. So now to solve for y, I will raise both sides of the equation to the 5th power. Because when y to the 1/5 gets raised to the 5th power, we'll end up with just y. In fact, it doesn't matter what that fraction is, 1/5. I mean, if that fraction ended up being something like, say, 23 over 100, instead of a 1/5, you saw a 23 over 100. I would raise both sides of the equation to the 100 over 23 power to end up with just a y. So raising both sides to the 5th power gives me 100 over 4.28 x to the 0.8. All of that mess raised to the 5th power. So now I can use my graphing calculator to graph it. So let me call up my graphing calculator here and see what the graph looks like. So let's see, and here I have to put this into y1. So I'll do parenthesis to contain my fraction, and then I always put the numerator inside parentheses and the denominator inside parentheses. So 4.28 x to the 0.8. So I have my numerator inside parentheses. My denominator's now inside parentheses. This parenthesis closes off the fact that that's a big ugly fraction. And I'm going to raise that to the 5th power. And now my viewing window. Folks, I have no tricks, tips, secrets for you here. When I look at these graphs, I always kind of start off by making a guess at the viewing window. For starters, I know I don't need negative values for x because x represents labor hours. That would make no sense, a negative number of labor hours. So I can tell you your x min should always be a 0. X max, okay, I'm going to make a guess here of 50, and then I'd probably scale by 5s. Since y represents the weekly usage of capital investment, it doesn't make any sense for y to be a negative number. So I can tell you that I'd always have y being 0. And my y max, you know what? I'm just gonna go with 600. And I'll scale by 60s. So I'm gonna hit graph. Hopefully I see something. If I don't see anything, then I'm going to have to come back and adjust my viewing window. Okay, so there's the graph. So here's what I need to do now, folks. We see what the graph looks like. I need to head off to the chalkboard and put that graph on the chalkboard to show you exactly how you need to have everything labeled in order for it to be absolutely positively correct. So I'm heading off to the chalkboard. All right, folks, we had just looked at how to graph this on the graphing calculator, and I said I was going to show you what you need to write down, how you need to present this so that it communicates exactly what you've done. So here's what you need to do. You take the graph that you see on your graphing calculator, make your familiar XY coordinate system. So you need to label that as X and Y, but you also need to label what X represents. And X represented the number of labor hours. So at least label the x-axis as representing labor. And then the y-axis was the capital investment. Then you look at the graph that was on your calculator and you just reproduce that graph and it looks something like this. And at the end of this, you need to put one more thing. You need to put Q equals 100. Because now what this tells everyone, or anyone that looks at the graph, it tells us that any point on this graph are all combinations of labor and capital that produces a quantity of 100 toys. So that is all important stuff. It needs to be on any graph that you make in this section. So let's head on back to the slides. We're going to find out that this curve actually has a name in the business world, in the econ world. So let's head back to the slides and find out what it's called. All right, so the graph that we just found in the previous example, in econ, that graph is called an isoquant. Iso is, I think it's a Greek prefix that means same, and quant is short for the word quantity, so same quantity. An isoquant shows all possible values of x and y for where q was the quantity was a specified quantity. So it's all, that previous graph showed all combinations of x and y that resulted in a quantity of 100 toys being made. A level curve, or some people call them a contour line, it is obtained from a surface. Now remember, surface, that's that three-dimensional graph, by slicing it with the horizontal plane z equals c. So that the previous graph we did, that graph, that isoquant, it was the result of looking at the graph of the production function, that three-dimensional graph, and if we sliced it with a horizontal plane of z equals 100, where that horizontal plane would intersect the graph of the production function. And then we graphed it in the xy plane. The equation for the level curve at height c is given by, well, you put c equals f of xy. So in the previous example, we had 100. We put 100 in. If we had taken the level curve of the previous example and we'd raised it 100 units above the xy plane, we would then see the behavior of the surface of the production functions 100 units above the xy plane. To see some ideas of this, what I'm talking about here, you can look in the book on page 647, figure 8.2.4, page 648, figure 8.2.7, and even page 649, figure 8.2.11. Those are three examples of, a production function or a function of two variables and slicing it with a plane, a horizontal plane, and producing a level curve. If we put a collection of level curves in the same coordinate system, the same xy plane, we end up with what is called a contour map. And that helps with the 2D representation of the surface. So a collection of level curves is just called a contour map. Exactly what we saw at the beginning of this video when we looked at a topographical map. So let's look at an example. It's the same example we've already looked at. So, we have the same production function. Q is still the number of toys made each week. X is still the number of labor hours. And Y is still the weekly usage of capital investment. So make a contour map of the function. And here we'll use C equals 40, 60, and 100. And if I do C equals 40, 60, and 100, it's taking the surface, and here's a graph of the surface, and slicing it with three planes that are 40, 60, and 100 units, the horizontal planes, above, the XY plane. And we're just going to see where those planes intersect the graph of the production function, and we're going to graph them in the XY plane. So, what I'm going to do now is I'm going to head off to the board to show you how to efficiently use your calculator to do this. Hey folks, in this example, we were still looking at the same production function from the prior example of, making the toys. Q's the number of toys, X is labor hours, and Y is the weekly usage of capital investment. And we're asked to make a contour map using C values of 40, 60, and 100. Well, keep in mind those are quantity values, 40, 60, and 100. In the previous example, we actually did the isoquant for a quantity of 100. Remember, a contour map is just going to be a collection of contour lines, or in this case, it's a collection of isoquants. So let's go through this process one more time. For a C value of 40, you put 40 in for Q, and to use the calculator, you have to solve for Y. So divide both sides of the equation by 4.28, x to the 0.8. And remember, 0.2, that as a fraction, that's 2/10, and 2/10 reduces to 1/5. So let me just change that to 1/5. And remember, you raise both sides to the 5th power to get 40 over 4.28 x to the 0.8. All of that to the 5th power is equal to y. That's what I will graph. That's what I will put into y1. Now, folks, let's be smart here and save ourselves some time. That's when we put 40 in for Q. Then we'd have to put 60 in for Q. So we put 60 in for Q. This would be a 60. This would be a 60. Our process of solving for y wouldn't change. So this would be a 60. This would be a 60, which means this is a 60. So for a y value of, or for a C value of 60, we're going to graph 60 over 4.28 x to the 0.8 to the 5th power. And likewise, when we put 100 in for Q, the 40 is going to change to 100. That's it. So that gives us 100 over 4.28 x to the 0.8 to the 5th equals y. So in my calculator, I would make this this y. I would make this y1 in my calculator. This would be, I put that into y2, and I put this one into y3. So I can graph all three of them at the same time. And we've already seen, I've already shown you how to use the calculator to graph one of these. You know how you have to enter it into the calculator. So if you do it, and you do it correctly, remember you have to say X represents labor, Y represents capital. You will see graphs that look something like this, and remember you have to label these. This is Q equals 100. This is Q equals 60. And this one here is Q equals 40. So that's how you make a contour map. We're only looking at isoquants, and a contour map would be a collection of isoquants. So that's it. That's all we're going to look at here in section 8.2. So you can go off and do the homework in section 8.2. Make sure you pay attention to how I've modified the homework assignment from what was on the academic calendar that I passed out at the beginning of the year, at the beginning of the semester. So I'll indicate exactly which exercises you need to do in section 8.2. But again, that's it for 8.2. Go do the exercises that I'm now asking you to do, and thanks for watching.